All right, so g of 3, so the easy way for that g of 3 just means put a 3 right there, right? So put a 3 right there, g of 3. So it's just the area for any time, and here's the big, like you were asking about starting it yesterday. The big hint is anytime you see a graph like that that's got like triangles and stuff like that, you're probably thinking, at least at some point here, I'm going to do area, right? I'm going to do the area under there and do triangles and rectangles or whatever, trapezoids, whatever the case may be. So anytime you see that or a half circle or something like that, right? That's a pretty good hint that, hey, I'll bet I'm going to do an area where I'm going to do a geometric formula. Okay, so g of 3 would be the area from -3 to 3. So that would be what? This triangle here, and then this triangle, and then another triangle over here. Let's see how good this is. So -3 to 3, so the first triangle is 1/2 times 5. 5? Oh, they did this whole big triangle. 1, 2, 3, 4, 5. 1, 2, 3, 4. So yeah, do this big triangle, that makes sense. And then this would be negative, and this would be 1 times 2 times 1/2. Got 9. Okay? Well, what intervals is the graph of g both increase and concave down? So what did we say about g? G prime was f. So g increasing means g prime is positive, and concave down means g prime is g concave down means g prime is decreasing. So we want something that's above the x-axis and decreasing. So from there to there, so from -5 to -3 probably, and then from -3, -5 to -3, and then 0 to 2. So right here, positive and decreasing. So 0 to 2. So there's your final answer right now. -5, -3, 0. Okay, and then this one, you do your quotient rule. So g prime times the bottom left alone minus g left alone times the derivative of the bottom, all times that squared. You get all this mess, plug in all your numbers, -1/3. Okay, and then this last one, so the derivative of the outside is f prime. Leave the x squared minus x alone, times the derivative inside, 2x minus 1. When it's all said and done, you get 6. Okay, very good. All right, number, what do we go to? 5? Then? All right, so you got all of this information. Find the x-coordinate of the local minimum, that's relative minimum, is local minimum from -2 to 3. Well, what do you need for local minimum? F prime to be 0, right? So F prime is going to need to be 0. Well, that happens twice, right? F prime is 0 2 times, and you need it to go do what? Negative. It needs a decrease. F needs a decrease and increase, which means F prime has to be negative to positive. So right here it goes negative to positive, so that would be out 1. Okay, out 1. Okay, now it says justify your answers. Now, this is interesting. This is just written there. One of the things that I talked about with local minimum, they've been very picky about the last few years on the AP test, is you should say that F prime switches from negative to positive, so therefore F switches, not cavity, from decreasing to increasing. So if F prime switches from negative to positive, F switches from decreasing to increasing. I think you should probably have both of that on there. Okay? Why must there be a value C such that F double prime equals 0? What's that sound like? The what? The mean value theorem. The mean value theorem. Oh, now wait a minute. That also sounds like the intermediate value theorem too, right? The intermediate value theorem, but the intermediate value theorem says it hits every point in between there, but that could be what's going on here too. But it also sounds like the mean value theorem. But let's look at this. I think it's the mean value theorem here is actually the one that it's doing, right? Remember, the mean value theorem is the one that said the slope between the endpoints, right? There's got to be some place where the slope. Okay, so if we're talking about, so where is F double prime have to be 0? Well, if you look at F prime right here, between -1 and 1, what do you have? Well, if you're looking at the F prime graph, if we were looking at the F prime graph at -1 it's 0, and at 1 it's 0, So who knows what it does in between? Well, we do know what it does between there. But anyway, the slope between the endpoints is 0. So therefore, there has to be some place in between there where this slope is 0. Well, the slope of f prime is f double prime. So that's what you would want to talk about, would be the mean value theorem. You'd say, since the slope of f prime between the endpoints is 0, there has to be some point in between there. And of course, it's because it's twice differentiable f. So f has both the first derivative and the second derivative. And remember, for the mean value theorem, it had to be differentiable. Okay? So that is what's going on there. So let's see what they say. F prime is both continuous and differential, therefore the mean value theorem, the slope between the endpoints, there has to be some point that equals that, but the slope between the endpoints is 0, because f prime and -1 and f prime 1 equals 0, so 0 minus 0 on top here equals 0. Okay, that's why. Alright, and we don't need to worry about words. Alright, the function h is defined by this, so h prime of 3, so we're going to do the outside, so that's 1 over f of x. So there's the 1 over f of x times the derivative inside, which is f prime. So you get f prime over f, and then you put in your 3. F prime 3 is 1/2 over 7, 1/14. Great? Okay, pretty easy. All right, and then what about this one? I didn't work it out. Oops. What about that right there? Did you get that one? Huh? That looks really messy. Now it looks like they did a U substitution. They did a U substitution, but I don't want to even mess with that. I'm hoping you just notice that. It's just a chain rule, right? I would hope you would just notice that the antiderivative is just that, right? Because I mean, look what that is. It's a derivative of the outside, f prime, with the g left alone, and then the derivative of the inside, right? So to me, the antiderivative of that, I would just hope we would just know it's that. But what do they do? I mean, it makes sense to do a chain rule on this, or a U substitution, let u be the inside, right? Now, we've never done one quite like that, but you let u be the inside, let u equal g of x. What's d? It's g prime of x dx, which is setting right there. So this whole thing becomes f prime of u du. So the antiderivative of that is f of u. They kind of wrote it kind of weird. Here it is, f of u. And they did 1, now they changed those numbers. Now you could go back to f of g of x, which is what I did, and then put in the -2 and the 3. But anyway, they end up with -6. Okay? I would have, what it would have looked like if I would have done this, I would have hoped to just recognize that the antiderivative of that is f of g of x, and then that's from -2 to 3. Then I would just put in, I would have had f of g of 3 minus f of g of -2, and then just that one there. But you still end up with that same thing. Okay? All right. That was it, right? All right. All right. Sample 3. Sample 3. Where is the sample 3? All right, is there any questions that we have not? Because there's at least one thing we're going to be able to do in some of these packets when we learn our new thing today. But is there anything left in sample 3 other than the ones that we didn't know how to do? Which one? 30. Is one we can't do. 30 is one we can't do. So, somebody was asking in the other class which ones were the ones we can't do. I think I said 26. Is 26 the first one? 20. I think 20 I said we couldn't do. Yeah. Okay. don't think there's any before that, is there? So there's 20, there's 26, there's 30, and then if we get into the free response, there you should be able to do all of 1, we should be able to do all of 2. We did 3 yesterday, except 3B, which I'm going to show you. That'll come later. That's a few weeks away. And then D we're going to do today, so you should be able to do the rest of 4. But D we're going to do here in a little bit. And then should be able to do all of 5, should be able to do all of 6. Okay? So, any... Any last chance? Last chance. Nothing?
You 28. Go back to like the A to the.
Yes. Yes. Did we not talk about this? Okay. Yes, it is. Now, there's a kind of there's a direct kind of work it, like Emily's saying, with the AE to the KT kind of business, and then there'd be kind of a non-calculus kind of, do you remember this from science kind of way to get it without actually doing all that. Okay, so let's look at both of them. So one would be, yes, definitely that you recognize, hey, that's AE to the KT, right? Now, what information is important in there that they tell you? And this is a no calculator. Initial population is 1,500, so what do I do with that? That's the A. That is exactly right. That's the A, only because at time 0, right, if you put a 0 in there, this would be e to the 0, which is 1, and that's why that is the initial population, okay? Like with Newton's law of cooling, that wasn't the case. I mean, we had to be careful. That's not always the case. It's at time 0, the Y would be 1,500, so the A would happen. And then it quadruples during the first 2 days, so what's that mean? Well, okay. That's the other thing I was going to say, that means it's doubling every day, but let's ignore that for right now. What does it mean for my equation?
T is 2.
When T is 2, this is going to be 6,000, right? Because it quadrupled. So now we can solve this. So we can divide by 1,500. Now this is no calculator. We still should be able to do this. So divide by 1,500, which is 4, and then do the ln of both sides. And then divide by 2. Right? And we get that right there. Right? Now, there's something, before I go any farther, there's something that would make my life a lot easier right now. What can I do with this 1/2 ln 4? I can put this 1/2 up there as a power. What's 4 to the 1/2? 2. So this becomes just ln 2. Okay? So now what do I got? Now I got y equals 1,500 e to the ln 2 times t. Right? Now what? Well, sort of. It to t, or what? You got to be careful. Yeah, the e to the ln 2 does, but what about that t? So what are you left with? 2 to the t, right? Because e to the, now you don't have to do that yet. But e to the ln2 raised to the t, that would be, because power to power you multiply, e to the ln2 is just 2, so this is 2 to the t, so I could do that, okay? Or, even if you didn't notice that, you could just put your 3 in now, right? Where do you put your 3? For t. So then, and if I move it around here, that'd be 3 ln2. Well, what's 3 ln2? That's ln8. That's ln8, right? And then I'd have e to the ln8, which is 8, right? So I'd have, either way, I'm going to have y equals 1500 times 8, right? So I'm going to put my 3 in for t. 3 ln2 is the same as ln8. You put that 3 in there, that's ln8. E to the ln8 is just 8. Or I could have done what you guys said first. I could have made this 1500 times 2 to the t. Then I could have put my 3 in there. And then 2 to the third is just 8. But anyway, it says, by what factor does the population increase? Factor of 8. Because the population was 1,500, now it's going to be 1,500 times 8. So a factor of 8. But I think Will said something right away, and some of you guys said that. If it says it quadruples during the first 2 days, that means it doubles every day. So what's it going to do after 3 days? If it's quadrupled in 2 days, one more day it's going to double again, which means it's going to be a factor of 8. So to be honest, you could have done this one without any of that calculus stuff. Well, and so you think that's probably what you did. Okay? And that's perfectly fine on that one, if that's what you did. Because you could do that. Now, normally they don't make it quite that easy, right? Normally they don't make it quite that easy. You definitely need to be able to go through this process here and use y equals 8, the kt, put numbers in, be able to solve, because sometimes it wouldn't work out so easy with that doubling factor. Okay? All right. Anything else? Okay, let's move on here. Yeah, 30 is definitely one we're going to be getting into probably next week. The lemon lab, we're getting close to slicing lemons. We're getting close. Probably Monday. You got a golf tournament Monday. Right. Just Friday. Probably thinking it might be Monday. Monday or Tuesday. Okay. So actually, it probably could have been this Friday, except for the fact that I'm going to be on TV. So. All right. Well, there's the GB. It's all right. So let's move along. So get your notes out. We're going to start chapter 7 right now. Start chapter 7. Yeah, field day, sorry. Well, the small school meets, what they do is they'll start at 8:45 with field events, and then the running events will start at like 11:30. Because number one, they got more kids doing multiple, like doing field events and running events. But more importantly, we have coaches that run off events. So the coaches will be running off the field events, and a lot of times the coaches time. They don't have a timing system or whatever. The coaches time. To where? And not usually. We used to. Yeah, we don't take very much. All right, so chapter 7. Okay, chapter 7. So chapter 7 is titled Applications of the Internet. Okay, or Using the Internet. So it's a lot like chapter 4 was, right? We've kind of come towards the end now of the interval. We've studied about where the interval comes from, which is adding up rectangle areas, the Riemann sum thing, infinite. Notice I put an approximation sign in there because the area under the curve is approximately the same as adding up a bunch of rectangles. Now, if we do an infinite number of rectangles, that would be the exact area. So we went through all that in chapter 5. Chapter 6, we studied about error and all that kind of stuff, about why the rectangles are off and how much error they commit and all that stuff. Okay, So if I was gonna draw, if I had a curve here, a function, I want to do some different rectangles, I've drawn some right rectangles in here, even if it's negative, we can add them up, and so forth, so on. Okay, so we know we can do area by adding up some rectangles. So chapter 7 is, okay, that's the integral, but we've already seen, we've already done some work on how we can use the integral. We've seen that it's a rate of change. If you do the integral rate of change, it's the net amount of change. So we've been talking about that. So we've already been using the integral for some story plots. Okay, so we really kind of led into chapter 7 here already. But chapter 7 is going to be some other ways we can use the integral. Some different problems where we can use the integral. But at its heart, an integral is this. It's this adding process, and adding up bits of whatever. And of course, in this case, it was area. Okay? So just like chapter 4 was uses of the derivative. Now, I think parts of chapter 4 were harder than chapter 7 is. I think we've already seen using the integral is pretty nice, because if we set it up, and usually it's with units, if we set up our integral, then we can a lot of times use our calculator to find that integral, and so it's good. All right, so let's take this picture right here. Okay, so go ahead and draw this picture. So I have two functions. I have the cube root function, x to the 1/3. I have the cube root function, and I have the parabola y equals x squared. So I'm drawing both of those in there. And so clearly, and there are some other areas too, but there is a definite little piece of area here that we might be interested in finding. Now, we've already talked about one way of finding this area, I believe, haven't we? I mean, one way of finding this area would be to do what? We did one problem like this. And this, we want to find where these intersect, right? So let me put my grid on here. I don't know if I didn't really use a grid, I guess, so I'll take that out. Okay, so this is the point 1, I believe. 1 squared is 1, cube root of 1 is 1. So that's their intersection point. So what could I do? What area? So if I drew a line right here, and I said, okay, here's this blue area. What's the blue area? That'd be the integral 0 to 1 x squared dx, right? That would be the area under the x squared graph. And then the green area, what would that green area be? 0 to 1 cube root of x dx would be the green area, right? And then take the green minus the blue, and that should leave me the blue. Now, what we're going to find is there's going to be times where it's not quite that easy to do that. That seems pretty easy to do. Okay? So we're going to look at it as an alternate way of finding that residue. Okay? So we're going to look at this like this. Okay? So go ahead and draw in those two little rectangles that I've drawn there. And doesn't it make sense that if we could do area before by adding up rectangle areas, we could do area again here by adding up rectangles, right? Doesn't it make sense we could stick some rectangles in there? Now the difference is before, our rectangles were setting where on their base? They were always on the x-axis, right? Our rectangles were always setting on the x-axis. Now they're not going to be. Now they're going to be, so our before, our f of x was, right, when we did f of c sub I times delta x, right, our f of x was our height, and our delta x was our width, right? Let me change colors back here again.
What's going to be our height? Like, what's the height of this rectangle right here? Let's call this, let's see, which graph's on top? Let's call this F. Let's call this one G.
G.
So it'd be this y value, which would be g of x, or let's call it c sub I, minus f of c sub I, and then times the width. So the width we would still find the same way, right? The width would still be v minus a divided by n. So we're still going to find our width, but our heights are not going to be just y values. They're going to be the top y value, right? They're going to be this y value minus this y value. And then that's going to be the height of my rectangle. And then if I take a sigma to add those up then, right, we're going to have it. So what's going to okay, so now it's just going to be a matter of finding it. Okay, so go ahead and switch to your homework. I don't know if you do homework on a separate page. You probably do. So let's switch to your homework page because we're going to do the first problem in the homework here. So number 1, and this is on page 420. And I'll give you the rest of the homework pages here in a little bit, but all right. So number 1 says, let R be the region between the curves y equals x and y equals x squared. Okay, so y equals x is just going to be a line, 45 degrees right through here. So let's just do the best we can. And then, so that's y equals x, right? And then we've got y equals x squared. So let's do a parabola. Let's really emphasize, let's really leave ourselves some space. So let's really keep it under there for a while and go up like so. We'll keep it really flat. Flatter than it normally would be, just so we give ourselves a nice piece of area there to be able to work with, okay? Otherwise, it's going to be this tiny, skinny little thing that's not going to have much area there. But this is the area we're going to look for. Now, where do those two intersect? One of the things you're going to find out is one of the things you're going to have to do, and this is where we'll use our calculators a lot, is we're going to have to find out where they intersect. Now, usually it's pretty simple. Usually it's pretty nice points. But sometimes it's not. Sometimes it's really ugly decimal values. And, of course, you use your calculator. But on one like this, what you can do is you can just set x equal to x squared, right? I mean, sometimes it's no calculator. So where is that? You know, take out an x. You know, so they intersect at 0 and at 1. Okay, so that's where they intersect. So sometimes you have to find it algebraically, whatever. So you find where they intersect. So we're trying to find this red piece of area. So it says to divide this up. So it says draw a sketch of the region, which we just did. So it said let R be the region between x and x squared. So we've drawn that region, and we can shade. You don't have to shade it because we're going to draw some rectangles in there, so I don't want to mess it up. But anyway, use 5 left rule rectangles to approximate the area. Now C says draw a picture. Let's draw the picture first. Let's draw the picture first. So, what do we need to find first to draw 5 left rectangles? The width. So, we got what? 1 minus 0 divided by 5. So, it's 0.2. So, 0.2, 0.4, 0.6, 0.8. Right? 0.2, 0.4, 0.6, 0.8. Now, I would say, we used to do 1/5, 2/5, 3/5 because we were looking for patterns. I think here use decimals because we're kind of let the calculator help us here at this point anyway. So, my first left rectangle is going to be where? So that's just going to go like that. So that one's going to be easy. Okay, let's go to the next one. at point 2. So what are we going to do? We're going to go up to the curve there and to the bottom curve there, and we're going to draw in this rectangle. Now, where do we draw from there? Okay, straight across to point 4 and down to point down and then across, right? So it's a little trickier to draw these, right? But you're gonna have 2 values. You got 2 curves, so you're gonna draw there, you're gonna draw there, and then you're gonna draw straight across like that. Okay, next one is gonna be at point 4. There'll be a dot there. There'll be a dot there. We'll connect. We'll go across to point 6. I just want to make sure you understand it does not necessarily hit the curve over here, right? It does not necessarily hit the curve at this other spot over here. We just go over to point 6, wherever that is, and it probably does not land on that curve there, just so you can see that. Then point 6, we go up to there, and go on the bottom curve. We go over to point 8, obviously. Pictures are not that, my widths are not very even, and then we're from there to there, and there's that last one. So my widths are not very good, okay? Right? So you get the idea. Okay, so now let's write that out. So what is my first rectangle? Now remember, the key is, you notice that really the key is identifying which one's the top curve and which one's the bottom curve, right? Because you want to do the top minus the bottom, right? Because to get that height, we want to be positive. Now, I forgot to say something here that is important. Whenever we do the area between curves, there's no such thing as negative area. In other words, the x-axis plays no role. What if I took, and I'm not going to be able to do this really well here, but what if I took this area, oh shoot. Okay, if I took this picture, if I took this graph and just slid it down a little ways, part of that area would go below the x-axis. That doesn't matter. The area is still the area. Okay, it's still this height minus this height. So let's say you had a rectangle that was, let's say you had a curve that was here at 1, and then it went down here to -1. What's that height? 2. 1 minus -1, right? It's a height of 2. That's why we always want to do top minus bottom. Our width is always going to be positive. Top minus bottom is always positive. We're always going to get a positive area. Okay? So the x, remember, so when we say the area under a curve, we always said that's the area between the curve and the x-axis, right? So up here was positive, down here was negative. Okay? And that has value because we can do net amount of change and all that stuff. But when we're doing find the area of this region between curves, always positive. Always positive. We ignore the x-axis in those cases. It's just from one curve to the other curve. Okay? All right, so let's start writing this out. So what is my height? Well, my height is my 2 left, so my top curve, so that'd be f of 0. Which one's my top curve again? I didn't identify it. Let's let f be that one. Let's let f be the top curve and g is the bottom curve. So it's going to be f of 0 minus g of 0. Now those are both 0. But then times 0.2, right? Plus f of 0.2 minus g of 0.2, and that's in parentheses, times 0.2, plus f of 0.4 minus g of 0.4 times 0.4, or no, times 0.2, sorry, they're always times 0.2, plus dot, 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 okay? There'd be one at 0.6 and there'd be one at 0.8, right? And then you could go to your calculator and you could get those. All right, the last part, so you'll get to finish that for your homework. The last part of the homework then says, and you can ignore the part in part C where it says something about underestimate. I don't care about that right now. Then it says find the area of R exactly using the fundamental theorem. Well, so what would the actual area be then if we had an infinite number of these? 0 to 1, f of x, which is x, minus, well, right, okay, yes. So back to what we were saying here. We would take this minus this, right? Now, if you do the integral of x to the 1/3 dx minus the integral of x squared dx, can't you put those together as one integral and just do that? And wouldn't that make more sense, right, than doing two separate integrals? So right here, if I wanted to find this red area, I could do the green minus the blue. Green minus the blue could just be put together as one integral. So that's what I'm going to do here. So I'm just going to go, okay, my top curve, which is x, minus my bottom curve, which is x squared, right? Like that. And now, according to the fundamental theorem, we would just do our antiderivative. So we would get 1/2 x squared minus 1/3 x cubed from 0 to 1, right? And then we would put in a 1, and so that would give us 1/2. Minus, put in a 1 there, is 1/3. And then minus, and then put in our 0, which would be 0. And we end up with 1/2 minus 1/3, which is 3/6 minus 2/6, which is 1/6. So that area would be 1/6. And then you can compare that to whatever you get with that when you finish it up, right? So I wanted to make that connection back to rectangles. Now, here's the thing. We're not going to do this very much. You're going to do number 2 in the homework. You're going to finish number 1 here. You're going to draw some rectangles. That might be the last rectangles we actually draw when we're doing these problems, okay? But I want to make that connection back to what we were doing with area. And I want you to see why it ends up being just the top curve minus the bottom curve when we set up this interval. If we want the area between these two curves, we just do the top curve minus the bottom curve, the top y value minus the bottom y value, because that would be your height of your rectangle. And then the dx, right, is what? The width, right? So it's like height times width. Height times width, just like what you have up here. Top curve minus bottom curve. So we just do top curve minus bottom. Okay? All right, now, so, our first result that we get today is if we're doing the area between two curves, and we just said that was 1/6, right? So the area between those two curves, and you might get your calculators out at this point too, okay? Go ahead and get your calculators out. Now notice I've written in there vertical strips. Now for us right now, we should think of that as vertical rectangles, but you're going to see why I called it vertical strips here in a minute. But vertical rectangles, which are the only kind of rectangles we've really drawn up to this point, okay? But it's a top curve minus the bottom curve, F minus G, or who knows what they're called, but whatever. Top curve minus the bottom curve. Pretty simple to get that area between those curves. And again, the x-axis doesn't matter. So if there is no such thing as negative area when we're doing this, right? Because that's why we do top minus bottom, because that'll give us a positive value. That's a bigger y value minus a smaller y value. So our height will always be positive, our width is always positive, so our area is always positive. Okay? Now, let's investigate an alternate thing. So now, go ahead and again, go back to your notes now. Go back to your notes. So now let's look at an alternate way to find this area. Okay? Now, instead of drawing actual rectangles now, well, I guess I could. I could draw one. Wouldn't it be possible to add up a bunch of horizontal rectangles, sideways laying rectangles, to also find this area? right? Now you might be thinking, why would you want to do that? What's wrong with the way we've been doing it? Well, you'll see there are going to be some cases where it will be much easier to do this than to do what we've normally done. So that's why we're going to look at it. But doesn't that make sense that we could add up and still get that area? Okay, now the question becomes, what is your height and your width? Well, now they're sideways. Well, let's still call this our height. Let's still, even though it's laying down, let's still call this our height. How would I get this height of this rectangle? And remember, I want it to be positive. Well, now careful. Okay, now keep in mind, we were saying y value minus y value, right? It's whatever this y value was over here and this y value here, we subtract it. So on this one, it's this x value minus that x value. Now, how do you get the x value out of y equals x squared? You square root the y value, right? In other words, we're going to know these y values, right? Because whatever the width is, right? We're going to know those y values. And with those y values, would this width be called delta x? What's it going to be called? It's going to be delta y. That's going to be change in y. And what we're going to want to do is take this x coordinate minus that x coordinate. So we're going to have to change our equation. Instead of f of x, it's going to be f of y. In other words, it's going to be x equals. Okay? And how would you get this one to be x equals? Cube that side, right? So to do horizontal laying rectangles, and we're not going to actually draw horizontal rectangles, but what we are going to do is we're just going to draw in a strip, and this is why I call it a strip. Because what happens to our rectangles when you do an infinite number of them? They're going to look just like little strips, right? They're not even going to really be rectangles. So when we look, so what we'll do is we'll just draw in a strip, and we'll call that, we'll draw in one usually. We'll just draw in one representative strip. And we'll think of that as our rectangle, and we'll think, okay, here's our height, so it's going to be this x minus this x, and then the width is always going to be the delta y or the delta x, right? If they're horizontal strips, remember, it's delta y. So what does that tell us? We're going to want to take this x coordinate. Well, what is this x coordinate? It's on the x squared parabola, right? So what is that x coordinate? What's the x coordinate? Square root of y, right? You know how on this, if we were back on this, if we were back right here, if we were at some point on this parabola, we call that x comma x squared. You know how we often do that with points, right? We got x and then our y. Well, what's our y? Our y is x squared, right? It's x comma y, but what's y? Y is x squared, so x comma x squared. Well, could we do the same thing here? Except with y's, could we say, okay, this is our y, and then what is this? Well, it's our x, but what's our x? Our x is equal to square root of y, right? So you're going to hear me say this to you a lot. I'm going to say, what is this x? What is this x value? And I'm going to want you to say, square root of y, right? I'm going to say, what is this x? And you're going to say, square root of y, because x equals square root of y. Just like if we're doing this one, I'm going to say to you, what is this y? What is this y right here? What is this y value? X squared, right? What is this y value right here? It's x squared. Because y is equal to x squared. See the difference? Okay, so I'm going to say we're going to take this x minus this x. Okay, so we're going to take this x minus this x. What is this x? Square. Now we're going to write that. We're just going to look over it. We're going to say, okay, what is this x? Square root of y. So we're going to have square root of y minus, then what's this x? Y cubed, right? What is this x right here? This x is y cubed. So it's going to be y cubed. And then the width is the dy. So you see how these are going to be in terms of y, not x's, right? when they're horizontal strips, are gonna be in terms of y, and it goes from what to what? Now we gotta be careful, our last one went from 0 to 1 because we were going this way, right? What's this one doing? This one's going up, but it's also 0 to 1. But a lot of times these numbers will be different. Now here's how I think of this. Here's what you're gonna hear me say a lot. Think of how the rectangles fill the space. Now I'm actually not gonna say rectangles, I'm gonna say strips. Think about it, but think of really thin rectangles of strips. How do the strips fill the space? The strips fill the space from 0 to 1. On the other one we were doing, the strips filled the space this way, from 0 to 1. Does that make sense? Okay. All right. God, I kind of miss that because I used to do this like this, and I used to say the strips fill the space, and I would do that right there. And then somebody in Mrs. Larson's room next door, because Mrs. Larson used to be next door, and then somebody on their side would bang on the wall. Back at me. But now I got nobody on the other side of the wall. I can bang on that wall and see if Boyd would. But he's got that, I think they've got that closet. So I don't think it's. All right. So, type this in your calculator now. Because you better get what? 1/6. Type it in and see. But what we had gotten earlier, what we had gotten on the other page, we had the square root, or we had the integral from 0 to 1, and then we had the top curve. Oh no, we're not going to get 1/6. This is a different problem. That was in the homework. We never did do this one on the other side, did we? So we're going to check it. So on this one, it should have been the integral from 0 to 1, and it would have been the top y value, which would have been x to the 1/3, minus the bottom y value, which is x squared, dx. So let's type both those in. Let's see what we get. Now, it turns out the calculator doesn't know. It doesn't care if you type in x's and y's, right? You can type in with a's or r's or q's, it doesn't matter. But I think it's a good habit to get into, just if you're doing one of these, do it with x's. If you're doing this one, do it with y's. Doesn't matter though. Okay? What do you get? 5/12. How much? 5/12. Did you do them both?
Yeah.
Both get 5/12, which makes sure we should. Which makes sense that we should. Okay? So think about what we're doing. So we've got this space. We're trying to find the area. We've learned how you can take an infinite number of rectangles and fill that space to get the area. It makes sense that they can be vertical rectangles or they could be horizontal rectangles. It shouldn't matter. And we can fill that space either way. And we can do it with horizontal, we can do it with vertical, and we can get that area. Now, probably we'll go with vertical most of the time because we're used to using X. So if you want to go back to your notes here. So the other thing we could put here is to find the area between curves, we can either do top curve minus bottom curve. That would be vertical strips. And those would be our normal strips. Those would have X's in it. Probably the easiest way to remember that is the vertical strips would have a delta X width. So that means there'll be dx. The horizontal strips will have a delta y width. And so they're going to be dy. So they're going to be in terms of y. So you got to remember it's right minus left. Because again, we want it to be positive. So we got to take right x coordinate minus left x coordinate. But it's going to be x equals some y. So it's like x equals square root of y, x equals y cubed, whatever. And so that's what we call f of y and g of y. Okay? Because they're in terms of y. All right. Now, notice here I used A and B, and here I used A and B, but those are usually different, right? I mean, a lot of times they'll put A and B, and here they'll put C and D. Just understand, if you go to horizontal strips, now your strips fill the space this way. Okay, so you're going to go from here to here in your image, as opposed to left to right. Okay, so important to understand the difference. All right, so let's take a look at this guy right here. Now, you do have your homework. In your homework, there's going to be a problem similar to this same picture, okay? So if you want to draw this in your notes right now, but then you're probably going to redraw it in your homework. we're gonna work it the easy way right now. Okay, let me see, do I have these? Yeah, okay, later. Okay, so here's our functions. Okay, we got, they actually gave them to you this way. They actually gave them to you as x's. Okay, now you can graph on your calculators. You can graph these. Actually, this is new in the newest update to the operating system. You can graph these functions here. They're called relations. If like a sideways parabola, right? Normally you would have to solve for y, get the y by itself to graph these things. So if we want to go here, let's go into our calculators real quick and let me show you that. So this can be helpful. To be honest, most of the ones we do are going to be simple enough where you could solve them for y and you could figure them out, I think, without your calculators. But if you want to do this, so let's go to our calculator screen. Let's go to menu. Let's go to graph entry, and let's go to relation. Okay? Now, notice it says relation x comma y. So what this does is it will graph any set of x's and y's. Now, what was that one equation I had here? I think one of those was x equals y plus 2. Now, look, it'd be very easy to subtract 2 there. You get y equals x minus 2. Well, it's got a minus 2y intercept, got a slope of 1, right? Very easy to draw that without your calculator. But let's just show how it does it. So that was x equals y plus 2. Boom. There it is. Okay? What's the other one here? The other one is x equals 1 minus y squared. So we can go, now again, it's possible you'll have to do this someday, somewhere on a no calculator thing, but on our quizzes, I'm going to let you use your calculator for it, so it's not a big deal. But now, so we tab, we go to our next one, and so we go x equals 1 minus y squared, enter, and boom, there's our parabola. Okay? And then, now, here's how the directions read on this. So this is very important that you guys are able to identify the region, because on a quiz, the problem's going to identify, it's going to lay out the region. You've got to find what the region is. I'm not going to help you. You know, you say, what are they talking about? Are they talking about this region or whatever? Here's how this would be worded. Okay, you ready? The region is bounded, oh wait, let me, it's back here. No, maybe it's not. Okay. Figure 4 says, oh yeah, here it is. Okay, here's how this would be worded. This would be worded by saying, find the area of the region bounded by x equals y plus 2, x equals 1 minus y squared, y equals 1, y equals negative 1. And they would give you those 4 curves. Now, that makes a pretty easy region to find in this case. Sometimes it seems a little more confusing. Sometimes it'll say in the first quadrant. Sometimes it'll say bounded by the x-axis, the y-axis, whatever. But remember I said, the x-axis plays no role here. We're just finding that green region. So just pretend that that x-axis wasn't even there. Okay, we don't care about it. Now, we can also graph, we can go onto here and we can graph y equals 1, which I'm not sure it's really that necessary to do on our calculator, but if you really want to see it, and then we can go on here and we can graph y equals negative 1, and we can get that whole thing. And there's that region. Now we get all these things in the way, which, whoops, that was bad. Okay, close enough. All right. And then let's get that label out of the way. Okay, so we're talking about the region bounded by all of these. So we're talking about this region, right? We're talking about this region in here. All right. Well, anyway, back to this. So that's under relations, graphing relations. If you have an x equals, it works pretty slick. All right. So back to this. So I've identified my region. Now, here's what you're gonna do in your homework problem. They're gonna say they want you to split this up into vertical strips. Well, now here's the problem. If I drew a rectangle, don't draw this in your right now. But if I drew a rectangle in here or a strip that was, say, right here, right? What's the top curve of that strip? Y equals 1. What's the bottom curve of that strip? This right here, right? But what happens if I draw a strip right here? The bottom curve is different, right? What if I wanted to draw a strip right here? The top and bottom are different, right? So to do this problem, you would actually have to split this into 3 different regions. You could do this region, now it turns out it's just a triangle, so you could probably just do a geometry, right? But you're going to set up an integral anyway. So top minus bottom. So these strips so you have to make sure that your strips, the top and the bottom, the right and the left, always hit the same curve throughout the whole region. So these strips would be the top curve here minus this line until you got to here. Then you would have this region and this region. So in your homework problem, you're going to find those 3 areas. There's a part A, a part B, and a part C that describes those. Okay, now, let me undo that. Here's what we're going to do. Oh no, it's undoing every one of those little dotted lines. Okay. All right, here's what we're going to do. Okay? What would be simpler? Horizontal strips, and this is what will be important for you to identify when you have your choice of what to do. Horizontal strips will be easier, because think about it. Every single horizontal strip I draw is going to do what? It's going to touch the line on the right side, and it's going to touch the parabola on the left side. You see that? So horizontal strips would be way better here to do this problem. So let's set it up. So, how do we do horizontal strips? We do the right x-coordinate. What is this x-coordinate? This x-coordinate is, remember what I said I wanted you to answer? Y plus 2. What is this x-coordinate on this line? Y plus 2. Now, if this wasn't x equals, we'd have to get it x equals. If this problem would have been written as y equals x minus 2 like that, then we would have had to get it as an x equals. Okay? So that's going to be y plus 2. You put it in parentheses, you want, doesn't really matter. Minus the left x-coordinate. What is this x-coordinate? 1 minus y squared. Now that has to be in parentheses. And then you stick on your dy for your delta y width, right? Don't forget the dy. And then it's going to go from what to what? -1 to 1. The strips fill the space starting from the lower end to the upper end. The strips fill the space from -1 to 1. Now you just type in your calculator. You don't have to do the fundamental theorem, even though you need to be able to do the fundamental theorem. But I'm going to let you just type in your calculator at this point and get what you get. Now, when you do the homework problem for this one, part A is going to describe this region, I think. Part B, like this region, and part C, this region, whatever. And then it wants to do vertical strips. And then you're going to add those 3 up and see that it gives you the same thing as that right there. Okay? All right. So that is how we do those. Okay, let's go to your sample 3 packet. And let's go to the 3 response.
Alright, so it says set up, but do not evaluate an integral expression that gives the area R. Now is this a no calculator or calculator? No calculator. So here's region R. Right? So again, we ignore the x-axis. Now, this has to be split into different regions, right? Are there any strips that are going to touch the same curves the whole time? Well, if you look at vertical strips, they're going to touch this parabola and this line until you get to where? Right there. Then they're going to touch this parabola and the line, right? So vertical strips before are going to touch this parabola and then the line if we do top minus bottom. Now what about horizontal strips? Well, horizontal strips would touch the parabola and the line until you get in here somewhere. Then you're going to have a little piece here that's going to be really confusing because this meets here. And then you're going to have this piece over here, right? And so the horizontal strips are not going to be good. Vertical strips are going to be the best. All we need to do is we just need to separate it right there, right? Okay, so set up but do not evaluate. So we're going to have our integral and it's going to start where? Well, it's going to start at A. Now, what'd you get for A? A is 1/2. Okay? Should already have that from earlier. And then it's going to go from 1/2 to 2, right? The strips are going to fill the space from 1/2 to 2. And then what are we going to put in here? This is F, right? This is this one, right? X squared minus 3. So isn't that going to be the top curve? The parabola is going to be the top curve. So that's going to be x squared minus 3. I can put that in parentheses if I want. Minus, and then what's the bottom curve? It's the tangent line, right? T. Well, some of you don't have this yet as I look. T said, give me how many days to ask questions about these and you haven't, nobody's asked about this. Okay? Well, I'll let you finish it. I'm not going to do the rest of it for you. So you got to find this tangent line, right? So you were supposed to do that in part C. So you got to find the equation of the tangent line. So you're going to do the top curve minus the bottom curve, okay, which is the line. Okay, so whatever you get for T here, okay, and that's it. That's going to be that part. Plus, what's the next part? From 2 to, what's that? 3.5. Okay, see, we're doing that part for some of you guys. Yeah, right back here, you're supposed to find A and B. Right, it was 1/2, and then it was 3.5. Is what A and B is going to be. Okay, so 2 to 7/2 or 3.5, and then what is it? Now what's the top curve? Now it's g of x, which is x minus 3 quantity squared, minus the bottom curve is the line, okay, that's t, you got to find t, tangent line, okay. But then it says do not evaluate because it's no calculator. They do this often, where they give you a problem like this, and then it's a no calculator one. So they're saying we're not going to make it, because here, if you were going to do this by hand, you have to FOIL this all out, you have to do a bunch of your power rule, you have a whole bunch of stuff, you got ugly fractions, it'd just be a mess without a calculator. So what they'll say is they'll set it up, but do not evaluate. So you set it up and then you're done. Okay, does it make sense? So that is how you do area between curves. Okay, let's go to your other packet that you have, the sample 4 packet. Let's go to that real quick. That was in 2014, I'm sorry, 2014, the one we worked on today. And let's go to problem number 2. And here we have this region R. Now this is the line y equals 4, right? This is y equals 4 up here. Okay, and then this is this function right here, right? So it says the vertical line x equals k divide, we're doing part C now. The vertical line x equals k divides R into two regions with equal areas. Write but do not solve an equation involving integral expressions whose solution would give the value k. So what does that mean? That means somewhere in here there's a line, right? Somewhere in there there's a vertical line, x equals k, that divides that into two equal regions. Doesn't it make sense? So what would be the area of the first region? These cross right here at 0, 4 together. So the integral from 0 to k Now, let me show you something here. On the AP test, when they have defined this as function f of x, or if they haven't, it's a good idea for you to define it as something. If they've defined that already as f of x, you do not need to write that all out. You can simply say that right there. You can simply go 4 minus f of x. Okay? Now, when you go to type in your calculator, obviously, you can type that in. Or on your calculator, define that as f of x. And then that would say good. Okay, we're not done though. Not plus. Well, it could be plus. But we're writing an equation. Right? So this area is equal to this area. Right? So it would be the area from k to what do you know about this point?
It's 4
The y is 4, right? Now this is a calculator problem. How are you going to find what this x value is right here? So I'm going to leave that for you, okay? So you're going to have to finish that. You're going to have, right? And then you'd have to go at least 3 decimal places. What do you do? Okay, finish it. Do what? What did you say? How do you find this? Emily's asking. Right, because you want the y, you want to know the y value on this curve when the y value is 4, because this is the line y equals 4.
So you said that equation right there.
So you put a 4 in for y
Do this one.
and do a solve, right? So you're going to find this value, and then what's it going to be in here? Same thing, because it's still, the strips are still 4 minus f of x. Right? Now, you could have done a plus. You could have said the area from 0 to k plus the area from k to whatever is equal to the area from 0 to whatever, the whole thing. That would have been an equation also. Now, it says do not solve, right? It says do not solve. So, set up that equation. If you solved that equation, you would find the k value, right? But you didn't have to. Okay, but what you do have to do is set this equal to 4 to find out that point right there. All right, so there's just a couple of examples of doing the area between curves. All right, so your homework here, you can go ahead and get started on, is in the top line here in chapter 7. Okay. Yeah.